So can everyone hear me okay? Maybe just message in the chat. Can everyone hear me okay? Can just people message in the chat? Or people not able to message in the chat? Oh, now you can. Can everyone message in the chat if they can hear me? Yep, okay, good. Okay, great. So we'll start. Sorry about that delay. So we'll talk about enthalpy. So enthalpy is the heat transferred at constant pressure, okay? So it's important to remember that. It's sort of similar to heat change, but it's just at constant pressure, okay? So that's the key thing. The next key thing is that it's kilojoules per mole, okay? So that's 1,000 joules per mole. So mole is a quantity of measurement where there's a certain number of atoms or molecules or ions. So it's that's how we measure it, and it's measured in standard conditions. And you should remember these standard conditions as being 100 kilopascals, 1 atmosphere pressure, and a stated temperature, which is usually at 298 K. Okay. So normally you get this sign where it looks like an underground sign or focal ball, sort of like a circle with a line through the middle. And then the triangle here means delta or change in H. The capital H is the enthalpy. And then that's saying at standard conditions, okay? So there's two types of reactions where you can have exothermic reactions, whereas negative delta H, yep, and that means heat is given out. Yeah, so think if you lose money, then that's negative. So it's kind of like exothermic, giving out heat. I know a reaction which is exothermic will actually feel hot, but that's not because it's gaining energy. The reaction is giving energy out. Yeah, so that's negative. And then endothermic reaction has positive H, okay? And that's because energy is taken in. Yeah, and if energy is taken in, then you can think of it as positive. Yeah, cool. So next we'll talk about lattice formation. Someone's asked how to get access to the lesson. I'll share this PDF with you afterwards, okay? Like I did for maths, if you were in the maths. So don't worry about that. But yeah, if you want to make your own notes during the lesson, that's up to you. But you will get this as well at the end. So lattice formation enthalpy, believe it or not, is the enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions. So it's in the name, really, lattice formation. So we're just forming that lattice, and that lattice is an ionic lattice, and it's always 1 mole for all of the formations, pretty much. And it's always from the gaseous ions. Yeah, so that's how you can memorize that. So those are the gaseous, for instance, sodium chloride, which is 1 sodium and 1 chlorine ions joined together in the lattice. You have 1 sodium plus and 1 Cl minus will join together to form this lattice, okay? This is exothermic, yeah? So we're giving out energy, so it's -787. You don't need to memorize these values, by the way, but you should then probably at least know that it's lattice formation is exothermic. So that is because bond making is exothermic, yeah? So you should remember that making bonds is exothermic, okay? So that's why lattice formation is exothermic, because you're making those lattice bonds, okay? And then endothermic is breaking bonds, okay? So endothermic will be breaking those bonds, okay? So that's that. And then the lattice dissociation enthalpy is basically the opposite of the formation. So you're going to go backwards now. We're going to go from this lattice and we're going to dissociate. Yeah, like if you dissociate with someone, you separate yourself from that person. They separate, the two separate, and they become separate. So that 1 mole of a solid ion will be dissociated into those gaseous ions, okay? So quite straightforward there. And this is opposite. So you should remember that if the forward reaction is exothermic, then the backwards reaction will be endothermic, yeah? So the fact that we're just doing the reverse of this one, and this was exothermic, then going backwards would be endothermic, okay? So now determining lattice enthalpy. it's kind of like what you're going to do here with the Born-Haber cycle. But just quickly, first of all, you atomize, and then you do the ionization energy, and then you do the electron affinity, and then you do the lattice formation enthalpy. Okay, so you do all those four things, and then you would get the lattice enthalpy formation. Okay, so that's that. We're going to get into that a bit more. So to get that formation, this blue arrow, first you have to do the atomization, which is this arrow up, and then you have to do the ionization energy, and then the electron affinity, and then lattice formation. And that's the whole formation of the lattice, okay? So if you just remember those four steps, then that would help. Now, these are lots of definitions that you need to memorize for enthalpies. So first one is enthalpy of formation. So you're just forming, yes, the enthalpy change when you form 1 mole of a compound from its elements in their standard states. You need to memorize that. Then bond dissociation enthalpy is the enthalpy change when all the bonds of the same type in 1 mole of gaseous molecules are broken. So you're essentially dissociating, you're breaking all those bonds. And then enthalpy change of atomization, you're forming a single atom from its standard state. So it's atomization, you're atomizing something, you're forming the atom, okay, from its element. And then the enthalpy change of atomization of a compound is exactly the same, but you're not starting from the element, you're starting from the compound. So you go from the compound to the atoms that were contained in that compound. And it's always 1 mole, yeah, as I mentioned before. And then the first ionization energy is when you knock off the first ion. So, sorry, you knock off the first mole of electrons. So you have an atom, like magnesium gas, you knock off 1 mole of electrons. So we don't write minus an electron to knock it off. We show plus electron on the other side. So that means that 1 electron is lost, and that's going to form 1 plus ions. And then second ionization is when you do that again. So we get the product from the first ionization energy, which was Mg plus. We knock off an electron, and then that would give us Mg2 plus, okay, plus an electron. Now, first electron affinity is the opposite of the ionization energy, okay? So now we're adding 1 mole of electrons to form 1 mole of 1 minus ions, yeah? And it's all gaseous for all this ionization and electron affinity. And then the second electron affinity, which by the way, we use EA for this electron affinity, and then IE for the ionization energies. And then that's just, you're getting the 1 mole of minus ions plus an electron to get 1 mole of 2 minus ions. And then enthalpy change of hydration is the enthalpy change when 1 mole of aqueous ions is formed from 1 mole of gaseous ions, okay? So you're just going from gaseous to aqueous, yeah? So all of them, atomization, formation, hydration, is sort of in the name, yeah? You just need to know in your head what that word means, and then you can get the definition from that. And then the enthalpy change of solution is essentially where you go from ionic to aqueous, okay? And that's an infinitely dilute solution, okay? So I'll leave these questions for you to do on your own afterwards when I touch it, but that would essentially be factual recall from the above. So now we'll go into Born-Haber cycles, okay? So Born-Haber cycles, you just need to memorize this structure, okay? So first of all, you have atomization enthalpies, yeah? And that's because this is the starting point, yeah? So this is the starting point of a hair. And then you can either go straight to the ionic lattice by forming it. So that's one route. So the blue route, this is Hess's law, by the way. Whichever route you take is the same, okay? So we can take the blue route to get from this start. Yeah, so you can kind of say this is the start. And then this is the end, okay? So there's 2 ways to get from the start to the end. There's the blue route, which is here. And then there's the red route, which is the long way around. It looks like the long way around because there's a lot of steps, but the energy is the same, yeah? Because you're ending at the start, same start and the same end point, okay? So the enthalpy change, I should say, is the same, yeah? So H1 is going to equal to H2 plus H3 plus H4 plus H5 plus H6, yeah? And then after that, you just need to memorize the order. First, you do atomization, yeah? So we get to atoms, gaseous atoms, and then we make the ions, yeah? So first you make the positive ions with the ionization energies, and then you make the electron affinities, okay? So you make the electron affinities, and you make the negative ions. And then you form, from those gaseous ions, you form the lattice, okay? So that's essentially the step, okay? The steps. So let's try do this then for Na and chlorine, okay? So obviously you've got the answer there, but we'll do it from scratch then, okay? So first of all, we start off with the start, okay? So the start was sodium in its natural state, okay? So that would be sodium, which is solid at room temperature. And then the chlorine in its natural state. And because we're only forming Cl, it would have to be half Cl2, because we know that the Cl2 is diatomic, okay? So chlorine is diatomic, so it will be Cl2. And then we form it, okay? So that's the formation, okay? And I'll do it in blue, actually, to show you that that's one route, okay? So that's a lattice enthalpy of formation, okay? You can say that's delta H1, and that's going to form our sodium chloride, okay? Solid. And then now to get to the above one, we're going to have to, probably going to have to go a bit smaller, but I'll do it quite small then. So first of all, we're going to have to atomize the sodium, okay? So to atomize it, it will become into sodium gas, okay? So you only atomize one at a time, okay? And then we'll atomize the chlorine, okay? So right now it's half Cl2. It will just become Cl gas, yeah? Just Cl gas. So that would be delta H2 and then delta H3. So this is, the first one we did was the atomization. This was the atomization of the sodium, okay? So this was a mistake, so it should be gas, or maybe I didn't write it clearly. So that should be gas, okay? So we're going from the solid to the gas, yeah? So that's that first step. So that's atomization of sodium. And then this one was the atomization of chlorine, okay? Because we went from half Cl2. So it's not an atom, it's a molecule. It's a Cl2. We're atomizing it. We're getting an atom of chlorine, okay? So that's the atomization of chlorine. And this bit stays the same because we're not doing anything to this, yeah? So it will just stay as the sodium gas, okay? And now we're going to ionize, okay? We're going to do the first ionization energy of the sodium, okay? I'm just going to write IE, yeah, for ionization energy to save time. And that's off the sodium. So if you remember, to ionize energy means you knock off one mole of electrons. So that would become the Na plus, okay? And it would stay gaseous. And then that would become Cl. The Cl gas stays the same, remember? Okay, then that would be delta H4. And then because now we're going to be going down, so far all of these processes have been requiring energy. Now we're going to be releasing energy. So this is going to be endothermic, where we're going to add one mole of electrons. So now that's going to be the first electron affinity of chlorine, yeah, because the whole goal of this is to form the Na plus gas and the chlorine minus gas, because those are the two gaseous ions which will form this ionic compound. And if you remember from the lattice enthalpies, that we form the lattice from the gaseous ions, okay? So the difference between the formation and the lattice enthalpy formation is the lattice enthalpy is just from the gaseous ions, but the formation is from in a natural state, okay? So this now is we could say this is the delta H lat, yeah, of the formation, okay? And then this would be delta H5 and delta H6, okay? Now the whole key thing about Hess's cycle is this, okay? This route here, this red route, yeah, sorry, this green route, I've done it in green, is going to be equal to this red route, because whichever route you take from this start to the end, it's the same. That's what Hess's law is. Whichever route you take, it's the same change, energy change. So the green route will equal to the red route, okay? So the equation then, if I leave that till I write the equation, but we'll rub it out afterwards, is going to be H2 plus H3 plus H4 plus H5 plus H6. So all of that root is going to equal to H1, okay? And if you want to rearrange for H6, then of course you can, yeah? And so I should have really put the deltas before, yeah, but you get the point, okay? So the key thing is that you just rearrange and then substitute and solve, yeah, for this. So all these values will be given, by the way, all of these values except one of them, and then you might just need to rearrange and find that one, okay? Which is maths, okay? Cool, great. Should the electron be shown? Okay, yeah, you're right. Sorry, I should have shown the electron. Yeah, because once we knocked off one more of electrons. So yeah, that should be electron. Good. Okay, thanks for reminding me of that. Okay, good. So that's that. Now next, you can do the same with magnesium. Okay, and you could draw the Born-Haber cycle for magnesium as well. But it would be exactly the same. Okay. But we'll do it anyway, just because this time it's not exactly 1-to-1, isn't it? Well, it is 1-to-1 actually. Okay, so it's the same thing, yeah, for magnesium. You can try that yourself, okay? But the difference actually this time is we're going to get 2 plus and 2 minus, okay? So you'd have to do the first ionization of magnesium. So in this part here, where we had the ionization of sodium, you'd have to do the second one as well, okay? And then the same with the ionization, the electron affinity of oxygen. Here you just did the first one of chlorine. If it's oxygen, you have to do the first and the second, yeah, to get to O2 minus, okay? So yeah, you do the second IE and the second EA, okay? Good. Now, the next thing we'll talk about is the theoretical and experimental enthalpies. So the difference between them. The key thing is this, okay, that there can be a difference, and that is because ionic compounds are not perfectly ionic, but they usually have some covalent character, okay? So that means they're not exactly spherical, and positive ions polarize neighboring negative ions to different extents. So the more polarization there is, the more covalent the bonding will be, okay? So just know that if there's a difference, then it's because ionic compounds have some covalent character, okay? So yeah, you could try this question as well, but it's pretty much the same thing that we did here with the Born-Haber cycle. And yeah, this is this one here, and it's pretty much the same, yeah, these type of questions, yeah? So, dissolving ionic lattice. So someone asked, what's covalent character as a definition? You probably won't be asked that, but it will go back to your understanding of an ionic bond and a covalent bond. So covalent bond, covalent character means that the electrons have not fully been lost and they're sort of being shared, if that makes sense, yeah? So that's sort of it, okay? So next, dissolving ionic lattices. When a solid ionic lattice dissolves in water, then that means you can get you get two things happening. So the first thing is that the bonds between the ions break to give gaseous ions, and that's the lattice enthalpy of dissociation. And then the second thing that happens is the enthalpy change of hydration. So then the gaseous ions become aqueous, okay? So this is the two things that happen. To get that, remember I said Hess's law, whichever route the reaction takes, the energy enthalpy change is the same. So we can just get directly the enthalpy change of solution, which is delta H3, but we can also take a different route, which is the lattice dissociation enthalpy, that delta H1, and then delta H2, which is the hydration, okay? But you have to do the hydration of the positive and the negative ion, yeah? And then from this, you'll get that delta H3, which is the red route, would equal to the other route, which is the blue route, okay? So delta H1 plus delta H2, okay? Okay, good. So these are a few examples. So you can clearly see the same thing that I said. The delta H3 will equal to delta H1 plus delta H2. Yeah. Someone's asking, is it mandatory to know this form? Yeah, I mean, if it works, any form that works for you from the formula or equations is fine. This is just the way I prefer to do it myself, actually, personally. So that's why I'm teaching it this way. But if you already know how to do it a different way, then that's fine, yeah? But I would double check that you could, from this diagram, you can get the same, or not from the diagram, from the equations, you can get the same values, yeah? 17. So this is the enthalpy change of solution. And that's H3 is going to equal to the H1 plus the H2, okay? And then you just add those values, okay? But importantly, you take the values as they are, yeah? So if they're negative, then you just add those negative values, yeah? Don't think adding it means you convert the sign, yeah? It still stays as negative, okay? But that's maths. And that's the same for another example. You know, the H3 is just equal to the H1 plus the H2, yeah? And those values will be these notes. I would advise you to practice and see if you could do the questions yourself, yeah? So perhaps you could hide this part and then on the diagram, just get the answers, yeah? Alternatively, just try these questions over here, okay? Cool, good. So now we'll talk a bit about entropy, yeah? So entropy is a measure of disorder, okay? So don't get mixed up with entropy and enthalpy. If you remember before, enthalpy was the energy change or heat transferred under constant pressure, okay? So it's more about energy change for enthalpy. Entropy is quite different. It's how much disorder there is, okay? So disorder is just maybe measured, for instance, gas is more disordered than solid. So that would be a way of thinking about entropy increasing. But it could also be temperature. Things which move faster and higher temperature is usually higher entropy, okay? The thing to remember is that generally substances like disorder, so things in the universe tend to increase disorder, okay? So entropy generally increases in the universe. So disorder generally increases. So if you were to walk into your classroom and you just started to throw chairs in the air, throw tables in the air, it wouldn't just magically fall down in a nice ordered fashion, would it? It would be in a disordered way. Yeah. So that's like a way of remembering that entropy, generally things tend towards disorder. You don't throw things in the air and then they have a disorder. Yeah. So for me, this is sort of like proof of God as well, because how can the universe have order? How can the universe have order if things generally tend towards disorder? Yeah, things generally tend towards disorder. How can we have all the laws and systems that we see around us without God? Yeah, but here's entropy. So physical state entropy generally increases, yeah, from solid to liquid to gas. And that's just something to remember. Yeah, as you can see, gases, things are buzzing around, so more disordered. Solid, you should remember that they have a sort of regular arrangement of atoms. Yeah. And dissolution also increases, dissolving also increases disorder. Yeah, so it's increasing entropy, okay? If you have more particles, more people, if you think it's more disordered, okay? So N2O4 forming 2NO2, the entropy increases, okay? Now delta S is the change of entropy. So we use a capital S for entropy. So it's going from the products minus the reactants, yeah? So you're looking at the change. So to look at the change, you look at the final bit and then you minus the initial. So products minus reactants, of course, will give you the entropy change, okay? So yeah, this is fairly straightforward. If you want the entropy change for this, then we would just do the delta S, which will equal to S products minus the S reactants, okay? So that would be 94.6. Okay, I need to disable annotations. All right, yeah, okay, all right, yeah. So yeah. Anyone who is annotating, you won't be able to do that anymore. But thanks for letting me know that you could annotate. So now 186 plus 8 plus, yeah, so you're minusing the reactants, which is a HCl plus the NH3. Okay. Is it being recorded? Yeah, it's being recorded, so you'll get the recording, okay? 94.6 minus 186.8 plus 192.3. So this will be minus 284.5, okay? Kilojoules per mole. Sorry, not kilojoules, just joules per mole, okay? Okay, good. So that's that. Yeah, you could just answer similar questions like that for entropy change. The next thing we're going to talk about is Gibbs free energy change. So Gibbs free energy change is to a measure where to see if whether a reaction is feasible, okay? So feasible means that it will carry out on completion, yeah? So feasible in English, if you were to know, means that it can take place, yeah? So for reaction, it's the same, yeah? So if a project is feasible, then that means it can take place. The opposite of feasible is not possible. It won't take place, okay? So if G is positive, if G is negative, sorry, then it's feasible, okay? And obviously, if it's positive, then it won't be feasible, okay? So a negative G doesn't guarantee that it will happen. Yeah, it just means that it can take place. Just because a project is possible, is feasible, doesn't mean that that project's definitely going to take place. It just means that if you had enough, if the conditions were met, then it could be possible, okay? So let's calculate the free energy change for the following reaction. So you do delta G equals to delta H, which has 117 kilojoules. Okay. I thought sorry, is someone not on mute? Let me ask that first. No. I thought people can't unmute themselves. Okay, never mind. No worries. Okay, if that happens again, then I'll see what I can do. So I calculate the free energy change for the following reaction at 298K. So we do delta H minus temperature times delta S. Yeah, so this is a formula that you can just substitute into. So it would be 117 times by 10 to the power 3, because it's kilojoules, minus, so this one, because we have temperature in Kelvin, your delta H, sorry, if you want delta G in moles, in joules, then you should use delta H and delta S in joules. And because our delta S was in joules, we have a choice. We can either convert our delta S to kilojoules and then use the formula as it is, or we could convert both of them to convert delta H to joules. So in this case, we decided to convert the delta H to joules so that they're in the same units. Okay, so it'll be 117 times 10 to the 3 minus 298 times the 175. Okay, and then that will give us the 64,900 joules per mole. And because it's positive, it's not feasible, yeah, at this temperature. Okay. So can you, if as we see, delta H minus T time delta S is dependent on temperature, okay? So essentially, we have delta G equals to delta H minus T delta S, yeah? So what you can think about is these different situations, okay? So we should think about delta G and then delta H. Or actually, let's think about delta H and then delta S and how that affects the delta G. Yeah, so temperature in Kelvin is always positive, okay? So cos temperature in Kelvin is always positive because you can never go below absolute zero, okay? So this delta T is always positive. So we're going to look at different situations. First of all, the situation we'll look at is this one, where you have endothermic positive delta H, okay? So if this is positive, so by the way, if I write positive VE, that means positive, okay? So positive delta H and a negative entropy, then we're going to do something positive minus a positive thing times something negative. So you're always going to be doing positive minus something which is minus times minus. So then G will always be positive. So it will never be feasible, okay? So I'll say that again. It will be positive minus something which is negative, which will always be positive. Yeah. So that means not feasible.
What?
Okay.
I have to charge it for you.
Okay. Whoever that is not on mute, can you turn yourself on mute? For some reason, I can't put everyone on mute. I think people can't unmute themselves except for a few people. Okay. All right. Never mind. So the feasibility here will now be not, yeah, not feasible. And that's because it's positive. Remember, negative is feasible, positive is not feasible. And now we can look at the next situation. We've looked at this situation. Now we can look at the next situation is if delta H is positive and delta S is positive, okay? So if this is positive, and then we're minusing something positive. So it will be positive minus positive. Then now it depends. If that positive we're subtracting is less than the starting one, then that would, it depends, yeah? So it could be positive or negative, yeah? So it depends on T. If T is large enough, then we would be subtracting enough to get negative, yeah? So instead of saying depends on T, I should really say if T is large enough, okay? If T is large enough, then it's feasible, okay? And then the next situation we have is we have positive endothermic and S is positive, okay? So we have positive and positive. Oh, sorry, we just did that one. Positive. So I think I've probably copied that twice. Okay, cool. So that's it, yeah? That's the next one. Oh yeah, then the next one. Whereas that if it's exothermic, is negative and negative. So if it's negative and negative, then it will be feasible below a certain temperature, okay? Because we're going to be doing negative minus something negative. So if we subtract something negative enough, then that would depend on, so if it's negative and negative, then you're doing something negative minus something negative. So if T is small enough, then it would be feasible, okay? Because we want to stay negative. So if T is small enough, then we wouldn't have added something taking us above zero, yeah? Okay, good. So that's that. And then I think there's another one where it's negative and positive, okay? So you could have an exothermic with a positive S, and you start off as negative, and then you're minusing something positive, you're always going to stay negative, okay? So it's always feasible. Okay, because you started off as negative and you're subtracting something negative, Yeah, if your bank account's negative and you're spending more money, then I'm sorry, you're just gonna stay negative, aren't you? So that's gonna be always feasible then, because we know G is feasible when it's negative, okay? I'll just make that a bit more clear. These lines here. Cool, good. So that was that bit here. So we have an example here then. The decomposition of calcium carbonate is endothermic, but results in an increase in entropy. Okay, so let's look at the example then. So it's endothermic. So delta H is positive, increase in entropy. So delta S is positive. So then we have delta, sorry, G, is it delta G? So delta G delta G equals to delta H minus T delta S. So we have positive minus something, because T is always positive, so it's going to be minus something, which is positive. Yeah. So as long as we subtract something big enough to take us to negative, then it will be feasible. Yeah. So it will be feasible above a certain temperature. Someone is asking, how do you remember it? You don't remember it. You work it out. Yeah, you think about the maths. You start with positive and then you minus something. Is that going to take us to something positive? You minus something negative, it's always going to take you to positive. So you don't memorize it, you work it out. Yeah, I would recommend working out rather than memorizing it. Okay. Okay. Now I'm not going to go through this section summary, but you can memorize this, yeah, or you should understand this checklist for yourself in the notes. I just went through it, so I'm not going to go through it again. We'll try some questions, okay? So the first one is determine the lattice, determine the enthalpy of lattice formation, yeah? So think about what that is. What definition would you give for that? So this is the enthalpy change when 1 mole, because we're forming, right? We're forming the lattice. So 1 mole of an ionic compound. So remember the lattice is basically an ionic compound. So we're forming that ionic compound from, where are we forming it from? We're forming it from the gaseous ions, okay? And you can even say ionic lattice, to be honest. They allow that in the mark scheme. Yeah, I should really say it's gaseous ions, yeah, but as long as you got something like that, they'll probably let you on, yeah? Cool. So use data 1. Use the data in table 1 to calculate the enthalpy of lattice formation of silver iodide. Okay. So we want the lattice formation of silver iodide. So that is the formation of silver iodide, which will be Ag gas plus I minus gas, because remember we're forming it from the gaseous ions, yeah? So we start off with the gaseous ions, and then we're going to Ag solid, okay? Agi solid. So first of all, to get from gaseous to solid, we can make both of them aqueous, yeah? So we can make the Ag, this one, we can make this one aqueous, and the energy given to that is minus 464, okay? And then we can make the I minus aqueous, which energy will be minus 293. And then if you add these two together, then actually we'll be going that way. We're just going that way. So if you go from the AgI solid to these two aqueous compounds, then that would be the plus 112. Okay. Now we want this, yeah, which is x. So there's two roots that we have equal to each other. We have this root, which is x plus 112. Yeah? So that would be x plus 112. And then we have the red root, okay, which is that root is going to be equal to minus 464 minus 293. Okay. So now you just rearrange and solve for the x, okay? So you just get x will equal to minus 464 minus 293 minus 112, okay? So that would be minus 464 minus 293 minus 112, which would be minus 869, okay? Kilojoules per mole, yeah, because that was all the units, kilojoules per mole. So the units stay the same as we had, okay? Does that make sense? Any questions on that? Okay, good. So now the next question, a calculation of enthalpy of lattice formation of silver iodide based on a perfect ionic model gives a smaller numerical value than the value calculated in question 1.2. Yeah. So remember I said that this difference occurs because there's covalent character. Yeah. So you should say AGI. So that's why it's all about just learning. If you have a good textbook, just spend time learning that textbook and then practice exam questions and you'll be fine. Yeah. So it's just a matter of investing that time. So AGI contains a covalent character. And that means that the forces and bonds are stronger. Okay. So so the perfect ionic model is smaller. So we have a larger value. So that means we are going to be stronger. Okay. The forces and bonds holding the lattice together are stronger. Okay. So identify a reagent that can be used to indicate the presence of iodide ions in an aqueous solution and describe the observation made. Yeah, so this is, I mean, it's from a different topic, but just so you know, you should test with silver nitrate and you'll get a yellow precipitate, okay? Yeah. So that's that. And then now we'll look at this question, okay? So this question is, we're making titanium IV, can be made from titanium IV oxide as shown in the equation. Some entropy data are shown in table 3. Use the equation and the table data in table 3 to calculate the Gibbs free energy change for this reaction at 989. Give your answer to the appropriate number of significant figures. Use your answer to explain whether this reaction is feasible. Okay, 6 marks. Wow, a lot of stuff for us. Let's see if we can finish that. So essentially we need the delta S, which will be delta S products minus delta S reactants. Okay, so the products will be the 2 times the CO, 2 times the 198, plus the TiCO4, which will be 253, minus the reactants. Now just put a minus with all brackets and you add it all up. So it'll be TiO2, it'll be 50.2 plus 2 times the carbon, which will be 11.4. It's 2 times 5.7, and then 2 times the chlorine, which will be 2 times 223. Okay. So we can do that to get delta S. Has anyone done that? Get our value. That'll be 141.4. kilojoules per mole. Unit, no, joules per Kelvin per mole, I should say. Yeah, but that's fine. And now we just do delta H minus T delta, so delta G, we're equal to delta H minus T delta S, okay? Now the delta H was minus 60, okay? But we should times it by 3 because over here we just have joules, okay? So it's not fair just to use kilojoules here and then use joules there. So let's make things fair and make this minus 60,000, yeah, because kilo means 1,000. So minus 60,000, then minus T, and T has to be in Kelvin, yeah? Kelvin. So to get Kelvin, you add 273, yeah, 0.15. Okay, so 989 plus 273.15. So that would be 1262.15. I can't remember if you need the 1.5 for your syllabus, but you can double check that for your A-level exam board. But it's only going to make a small difference. So it'll be minus that 1262.15 and then times by the delta S, which is 141.4. Yeah. Did I type that in correctly? Is that okay? Okay, all right. That's fine. Assume that I typed in things correctly. If I made a calculator mistake, then forgive me, but the main thing is that you get the method anyway. And hopefully you'll type things correctly in the exam. So the main thing now is that this is negative. So it'll be minus 238,468.01, which is less than 0. So it is feasible at this temperature. Remember, delta G less than 0 is when it's feasible at this temperature. Okay. Yeah, we have a Born-Haber cycle question here. So it just wants us to write the missing symbols on the appropriate energy levels. Okay. So we've done the atomization of the magnesium. No, sorry, of the oxygen and the magnesium. And then now we're going to have to get Mg plus gaseous plus the O gaseous, and then we're going to get a plus an electron, and then we're going to get Mg2 plus because we're going to do the next ionization energy. This was IE1, and this will be the second ionization energy of Mg. So that means now we're going to have 2 electrons, and then we're going to have EA1 of oxygen to get O minus, and then that will become Mg2 plus O. Oh, so I should really have a G there. Plus O minus, okay? G, and only 1 electron, because we've absorbed one of the electrons into the oxygen. So there's only 1 electron now. And then that electron will be absorbed into the O minus to make O2 minus, and then you have this. Yeah, I think we've run out of time, so we'll leave it there. Sorry that we started late. I would have liked to make up the time, but I've had to go. So I would recommend that you just go over the notes again. I didn't answer the questions in green, but even the questions I did answer, you can do them again. And those ones that I didn't answer, you can do them for the first time. But yeah, really, you need to revise all the topics like this to the best of your ability. And that will put you in a good situation for the exam. Yeah? Is that okay? Cool. All right. Great work. Thanks. Bye.